Ball B is stationary, while ball A moves horizontally to the right. And you can see that the distance between the balls A and B keeps changing at every instant. We have to find the minimum distance between the balls A and B. We know mathematically that if we drop a perpendicular from B onto the path that A travels in, we would obtain the minimum distance. But let's try to reason this out using the velocity of approach. We take an arbitrary position of ball A at a point where the line joining A and B makes an angle theta with the line along which A travels. The velocity of A, VA, is along the horizontal line, and we resolve this into its components, one along the line AB and the other perpendicular to the line AB. And when we use the velocity of approach concept, we are interested in only the component along the line joining A and B. We take the component along the line joining A and B, which is VA cos of theta, and since this points towards B, it is the velocity of approach. As the ball A travels to the right, it is clear that the angle theta will keep on changing, and therefore it would imply that the velocity of approach would also keep on changing, both in magnitude as well as in direction. Let's watch what happens as ball A moves to the right. The velocity VA would have the same magnitude and direction, that is, to the right. But as you can see, its components VA cos theta and VA sin theta keep changing. Let's watch this one more time. We are interested in VA cos of theta, and as you can see, initially it points towards B, so this is the velocity of approach. And then it points away from B as it crosses the perpendicular, so this is the velocity of separation. So what's happening here is the velocity of approach changes into the velocity of separation, but both are computed using VA cos of theta, as that is the component which lies along the line AB. If we run the animation up to the point where the line joining A and B is perpendicular to the path of A, we can see that at this point theta is 90 degrees, and therefore VA cos of theta is 0, which means that the velocity of approach reduces down to 0. And as the ball A further travels to the right, this will change into the velocity of separation. So mathematically, in order to find the minimum distance, we need the velocity of approach to be 0, and in this case it occurs when theta is 90 degrees. So anytime the distance between two particles decreases and then increases, the velocity of approach must come down to zero at some instant where the distance between the two particles is the minimum. Similarly, if the distance between two particles increases and then decreases, the velocity of separation must come down to zero at the instant where the distance between the two particles is the maximum. When the distance between two particles decreases and then increases, when it is at a minimum, the velocity of approach will be zero, as it changes from the velocity of approach to the velocity of separation.